Pathfinder。またお前か。前回はよく戦ったが、今回はお前を見せしめにしてやる。お前が与えた苦しみの声を蹴るときだ。今度は絶対に負けない。やってみよう。先生、彼には勝てない。彼は強すぎる。トマス、バックトロフィールドを使い。いや、俺はあいつを倒す方法を知ってる。
So by now I've gotten a few comments on my previous videos disapproving of my use of AI to write some of the code in my projects. Now I still think that AI is a great tool for getting videos to you faster by helping with turning my ideas into code as well as generating visuals for that skit you just saw. Now that being said, I can also understand if for some it feels like watching a chess grandmaster play whilst knowing that Stockfish is whispering all the correct answers up his... Oh, forgot I left that in there. I'll say more about the role of AI in programming towards the end, but besides that, this video is about a coding problem that I have been struggling with for years, and I want to build it from the ground up, because this time, it's personal. And today, I think I might finally know how to beat it for good. So with that in mind, if Nimrag659 clicked to see it built from scratch, then let's build it from scratch. Before I show you my new idea for pathfinding, let me just show you where I've been so far. So my first attempt at pathfinding went something like this. Here's our enemy, here's our player. I had a circle around the enemy and the player like this. I'd get random points in that circle, and then I'd check if it could see the previous point in the path. And that tended to generate paths kind of like this. And obviously you wouldn't want it to follow this path. So then what I would do is I would have another algorithm that would simplify this path. But as you can imagine, this was outrageously inefficient. And when I tried using this for my game Numicron, it was just an insane amount of time just for one enemy to find the path. So this was a fun first time dipping my toes into these waters, but it still wasn't too great. So what I tried next was the A-star algorithm, and there's lots of videos out there that explain this pretty well, but just to give a brief rundown, what A-star does is it takes a collection of nodes, and these can be nodes in a grid like for most games, and if you want to figure out a path from one point to another point, what it's going to do is search the nodes immediately next to it and add the distance from your current node to the next one plus your estimated distance to your destination as the crow flies. And as it traverses and checks each of these nodes, in the background it's adding up those distances in order to figure out which way is going to be the shortest path to the destination. Now this was a pretty good algorithm to use in my game, but there were a few downsides to it. If you had multiple enemies on the map at the same time, you have to rerun the algorithm for each enemy individually. And A-star is pretty efficient, but that can kind of stack up. The second main issue is that when the terrain changes, let's say that this enemy's path on the previous frame goes through these tiles in order to get to the player, well that's no longer going to work because this wall is now in the way. So every time your terrain changes with A-star, your paths are no longer really guaranteed to work, and you'll have to regenerate them from scratch again. I have a couple of goals with my new idea for this pathfinding algorithm. So first of all, I want to make something that scales well with lots of enemies. And secondly, while A-star works well for static environments, I want to make something that can easily adapt to changing environments. So here's what I'm thinking. Let's say we have a spaceship. So inside the spaceship, since we haven't all uploaded our consciousness into robots yet, we have a bunch of air molecules inside of here. What's gonna happen when we open the latch and let this air out? Because the pressure inside the cabin is greater than the pressure outside of the cabin in outer space, these air molecules right behind the entrance are going to be pushing on the ones next to the entrance to get out. And as those air molecules flow out, it creates a lack of pressure, which causes these ones to start flowing out as well, until the whole cabin has no more pressure in it. None of them really know which way they need to go in order to get out of the cabin, but because of the lack of pressure that propagates across the cabin, they all end up finding their way out. They just follow the stream that's been created by the lack of pressure at the cabin opening. And this is the idea that's going to inspire our new pathfinding algorithm. Now, I'm not sure if this idea will be just as or even more efficient than A-star, but I thought it was interesting enough that it'd be worth trying it out anyways. Now let's bring back our grid. We have our player here and our obstacles here. Now, in order to pathfind in this environment, we can consider the player's position as being the place where there's negative pressure. And everywhere where there's a wall, it is kind of the source of pressure that pushes out out on each side where there are empty tiles. And now what we'll do, just like in the spaceship analogy, we'll start at the place with negative pressure and we'll propagate outwards. So let's say we start with a tile right above him. It has pressure coming from this wall over here and this wall over here. Those two cancel out, and it has pressure coming from up top, and down below it, since there's a place of negative pressure, we just ignore that space instead of adding anything to it. So in the end, the vector for this tile points downwards, and we can do the same thing with the rest of the tiles, kind of spiraling out from that one position. This is how the grid will look when it's all filled in and the pressure has propagated. So just by following the vectors to the next tile will eventually lead you to the player no matter where you are on the map. Now, a couple interesting things to note. First of all, with certain environments, you can get places of neutral pressure like this, and in that case, what we would just do is choose a random tile adjacent to it that already had a non-zero vector when it was created. And also, you can see that when there's environments with rounding corners like this, it leads to the vectors down here not really choosing the most efficient path. For example, instead of this one going here, it'll instead go diagonally up and then down. So that's a potential downside that I can foresee possibly being an issue. I'm just interested to see how this will perform. So I'll call this method the pressure-based Pathfinder, and that's all the explaining that I have. Hopefully that makes sense. So let's get down to coding. Time lapse in 3, 2, You know, I once saw a comment on a Sebastian Lag video saying something like, every Unity programmer inevitably has to write their own visualization animation library. So I just finished writing this script to animate a 2D grid, although I'm not sure why these lines are sometimes ending a little bit before they touch the very end. Not sure why that's going on. Okay, so I just finished coding another little part of the script to put in walls wherever I click on the grid using this little pastel color, and you can remove them too. Perfect, so far so good. By the way, do you ever find it annoying when Visual Studio puts this little extra line beneath the code? I just can't stand it. I always delete it. It's like deleting the default cube in Blender. Bro, no way this worked first try. So now I've got a function that can essentially visualize drawing arrows. Nice, nice, nice. We can make like a Millennium Falcon hyperspace looking kind of thing here. I don't even know what to call it, but it looks cool. Okay, now we've got a bunch of little arrows all over the grid that point to my cursor. We've got a few bugs still with this. It seems that the head of the arrow kind of lags behind the body of the arrow. I can't seem to figure out why that's going on, so if any of you can figure that out, I'll give you $1 million. And besides that, I also can't figure out why when I set it to maximize, the body of the arrow just disappears and it only leaves the head of the arrow. Kind of a strange bug. I'll give you a winning lottery ticket if you can figure that out. Okay, now that we've got some decent visualization tools coded up, let's go ahead and implement the actual pathfinding algorithm. Now when we press P to pathfind, whoops, oh, that bug's still there, I forgot about it. But you can see now the arrows of where the path is pathfinding to propagate outwards. And now they all kind of point in general to the center. Now we should be able to place some walls around here. Oh, wait a minute, hang on. It seems like it's working for the most part, although I think points like these are the points of neutral pressure. I did put in some logic to deal with those, but I think that's still a bit buggy. But for all the other ones, it looks like it's generally working. All the way over here, you can see these guys. Oh, I wonder what that's about. Still some stuff to figure out, but we're getting pretty close. So I fixed the bug with tiles that had neutral pressure. It was a pretty easy fix. All I had to do was just take this not equal sign and turn it into an equal sign. But on here, I have also found a flaw in my algorithm. Let's say we have our 3x3 tile again. Here is where we're pathfinding to, and here is a wall. Now remember, we use surrounding walls to dictate where the pressure vector goes to. And then down here for this one, what happens is it goes this way instead, because it's just getting the pressure from here and here. So in order to prevent that, I thought of kind of an elegant solution. Maybe, we'll see. But what we'll do instead is we will kind of label the generations in which the vectors are produced. So for example, these are first generation, these are second generation, because both of these were the neighbors of these first generation tiles, and then these are third generation because they're neighbors of these. And now here is the important part. When this tile gets calculated, it'll go this way as normal, and then when this tile gets calculated, it will ignore calculated tiles of the same generation, meaning that the pressure from this wall will come through because this is a same generation tile, and because it's being generated on the same generation in the same column, it's kind of messing up our calculation for this guy down here. So by ignoring this tile, we can generate that vector as it's supposed to be. Essentially how we'll implement this in code is these guys will be calculated and then they'll be applied at the same time. These guys will be calculated and then applied at the same time. And then these guys will also be calculated at the same time and applied at the same time so that they don't interfere with each other. So that is how we're going to do it. Okay, I'm done thinking. I think I know how to implement this. I believe that should work, but of course we can only hope. So now what should happen if we place a wall here and we... Hey, there we go. Looky there. Now this vector used to be going diagonally and now it's going straight that way. Cool, cool, cool. Oh, I just love that animation. Uh-oh, what happened there? This one's going that way as well. Okay, looks like we're still gonna have to do some smaller tests and keep updating it. So as you can see here, when I have a wall and then I put my pathfinding origin on the diagonal point of that wall, the opposite end comes to point to that wall, which is not what we want. I've been thinking about this for a little bit. I can't think of another elegant solution to the algorithm. I think this might just be an inherent flaw to the algorithm, but I did have a couple of ideas because I thought of a simpler way to do it, and I'm not sure why I didn't think of this earlier. Pulling up Paint again. We can actually simplify the algorithm by doing this. So here's our pathfinding origin. Instead of taking vectors from the walls like this and summing them together, we could just sum together vectors pointing to its neighbors that already have calculated vectors. So for example, the neighbors of this one are this one, and this one. And only this one has its vector calculated for it since it's the origin. So our sum is just that. And same thing for here, and here, and here. And now we check the neighbors of this tile, which are this one and this one. This one has two neighbors, here and here. So we sum this vector, and we get this. And then the same thing happens here and here and here. The only problem with this is if we have this setup again, when we get to calculating this tile, we still get that same annoying vector that points to the wall. So what I'm going to do is if any tile has a vector that points to a wall diagonally, or that tile is just a neutral point, then we're going to assign it to just go in the direction of an adjacent tile that already has a calculated vector there. Problem solved.
The problem is solved.
Wait a minute, are these operators yellow? They're such a faint yellow that I always thought they were white. Unrelated, but whatever, just caught me off guard. It's too bad though, yellow's disgusting. I think I've finished implementing that idea for the simplified version of the algorithm here. I'll do my best to explain how it led to these triple Heartstopper burger chunks of code, but to be honest, if you can understand this part, you're a 150 IQ casual viewer pleb, and if you can understand this part, you must be a 300 IQ subscriber. I mean, there's just no other way. If this isn't god level 4th dimensional programming right here, I don't know what is. So first we calculate the vector in the x direction, and if the vector to the right exists, it gets a 1, and then we subtract 1 if the vector to the left exists. So if both vectors exist, it'll cancel out. Otherwise, it'll just end up being a 1 or a -1 pointing to that direction. And that's essentially the same thing that's happening with the y, but just on the other axis. And now this big boy, I did some really funky things with the ternary operator here. Honestly, I almost guarantee you that ChatGPT could not come up with something so hyperdimensionally dense. So here we go. For the default path vector, if the tile above the current tile is not 0, then we set it to be a vector going there. Otherwise, we set it to this. And what does this return? It returns if the vector to the right is non-zero, then it returns a vector going there. Otherwise, it returns this. And what does this return? If the vector on the tile below it is non-zero, then it returns a vector going there. Otherwise, it returns this. And what does this return? If the vector to the left of the current tile is non-zero, then it returns a vector going to the left. Otherwise, it returns vector2 dot 0. End parentheses, end parentheses, end parentheses. Booyah! Okay, sorry to flex, but that is just a brain twister. If any of this doesn't make sense, just rewatch it until it clicks, and I guarantee you will become a maestro 4th dimensional programmer also. I promise. I'm honestly not sure how I could possibly write this kind of code, and yet I can't solve most of those brain teaser puzzle chain link things that you can get at like Walmart for $2. I mean, the only times I've solved them is if I either get lucky or just get frustrated and break out the angle grinder. Okay, so now if we place down some tiles. Oh yeah, there we go, baby. Programming for the win. What I want to do, which I think might be pretty exciting, is testing to see how it performs compared to A star. Don't you just love when you've built up a whole code base and now you're tearing it up from the roots to refactor it and you get so many errors? Yeah, I love it. And if that's you too, I salute you. I've trimmed down the fat on the Pathfinder script so that it's only got the functions necessary to actually do the pathfinding, and it does it instantly instead of taking time to do the visualizations. And bonus, no errors. That doesn't happen very often. And now you can see when I click Pathfind on this square, they all show up instantly. It's a for loop. Inside of a for loop. Inside of a for loop. Whoa. Okay, that's way too big. Maybe we should tone that down a bit. What you're witnessing right now is the visualization for the A star pathfinding algorithm, finding the optimal path to the point where my cursor is at for every single tile in the grid. It just goes through each one until it gets to there. Now I took the script for the A star pathfinding algorithm, I ripped it out of my app, the game that I published in an earlier video. I'm not 100% sure if it's the best implementation for this algorithm, but it at least works in the A star way. Now let's just change this to a regular void function, and we will take out the waiting statement. And now when we set up our terrain, it should get all the paths simultaneously. There we go. Oh, that looks cool. That looks real fun. Oh yeah. That's just mesmerizing. I could do this all day. So now what I want to do is test the two algorithms against each other to see how they perform in terms of speed. For my algorithm, just by its very nature, as it propagates, it finds all of the possible paths in the grid to the target location at the same time. Whereas with A star, it only finds one path at a time. I have an idea of how we could modify it a little bit to find multiple paths at a time, but we'll get to that in a bit. So for my first test, if this is our grid, so we'll first run to see how much time it takes for my algorithm to find all the path vectors to the target location. And then what we'll do is we'll have A star pathfinding just run normally, and since it only finds one path at a time, we'll just have it start iterating over all of the empty tiles and finding paths individually for each of them and see how long it takes to do that for all of them. So for example, if we start at this tile, and then that's done for that tile, and then it'll move on to this one, and then same thing for here, and then here. And then same thing for the rest of these. You can already kind of see how we can make this a little bit more efficient, because if we start here with the A-star pathfinding algorithm, once it finds this path, you've found the path for this, but you've also at the same time found the paths for these tiles as well. So what we could also do to give it a little more of a fair test is to keep track of every single tile that it passes along the way and count those tiles as having their path complete as well. But I'm going to try the first idea first before we try that one, just to see kind of what happens. By the way, look how simple this is. With my function, just one line to get all the possible paths, whereas for the A-star, you have to do double for loops to iterate over all the tiles to get paths for all of them. So I put in some lines here to get the start time before the A-star paths are calculated, and then to get the end time, and take the difference to figure out how long that function took to execute, and then the same thing for the pressure pathfinder, and then we'll just see what it says. So if we start there, okay, A-star time, 0.026 seconds. Pressure pathfinder time, 0.007 seconds, baby. Let's go! The system, as I mentioned, explaining earlier, is a little bit redundant for A-star. We'll do another test with it, with that fix that I was talking about. Before we do that, I wanted to do a test with walls to see if it makes any difference. So why don't we do something fun? Okay, let's make a maze now. And then we'll pathfind from here. Oh, that looks cool. Oh, that's 12 times faster. 1,200%. Buy my stock. Okay, let's do something like that. Now let's pathfind. That was about the same as the empty grid, I think. Let's make the A-star pathfinding algorithm a little bit more efficient though now. We could even make this more efficient possibly by making it so that when new paths are generated, if part of that path comes across a point that is already visited, then we can just stop generating the path altogether and just kind of stitch together those two paths, if that makes sense. I'm not sure if it does without drawing it out, but that's just kind of beyond the scope of what we're doing with this project right now. And I think this is enough to give it a fair shot to compete with my algorithm. So let's see how it does. We'll start with the empty grid again and find. Yeah, so our other times are like 0.021 seconds for the A-star algorithm on the empty grid. And here you can see we brought it down to 0.01. We cut down the time by almost half by doing that. Looks like our algorithm still beats it, but at least that gives the A-star a little bit more of a chance. I do wonder why the arrows weren't drawing. There we go, that should fix it. And boom. Whoa, what was that? The devil and his dog are in the details of this program. This is just too much. Oh, I think I know what to do now. Now this should work, hopefully. Here we go. Now we've got some pretty little visualizations for where the paths are. Overall, I'd say that's looking pretty nice. Now what I want to do is I want to kind of add a tally where we can test these different algorithms in multiple different situations and kind of get an idea of what the average performance is. Actually, I think I was misinterpreting the speed results from earlier. This calculation is actually not correct. If we have a process that takes 100 seconds and we take it down so that it only takes 50 seconds, I was just saying, oh yeah, let's just divide the 100 by 50 and we get 2 and then multiply that by 100 and then you'd say 200% faster, but it's not. So it cut out 50% of the time. So it's only 50% faster. This is not correct. What we actually need to do is take this original time and subtract our new time and then divide that by our original time and then multiply that by 100, and that'll give us our 50% increase. This is the correct calculation, I think, in order to figure out how much faster our algorithm is from the A-star algorithm. Glad I caught that, because I can already see people calling me out in the comments section. Hey, this is Future Thomas going interstellar mode to make yet another correction. So it turns out that when saying A is X% faster than B when talking about algorithms, the terms can get a little bit ambiguous and confusing. The equation that I just showed you actually calculates the percentage of time saved, not the percentage by which A is faster than B. So in the rest of the video, when I say X% faster, what I mean is that we saved X% of the time. So if one algorithm runs in 10 seconds and we reduce it to 5 seconds, then we saved 50% of our time, or we reduced the time running by 50%. In order to figure out how much faster an algorithm is, we need to use a different method by calculating the speed of the algorithm in terms of tasks per second. So if our first task took 10 seconds to run, then we can say that it ran 0.1 tasks per second. This one did it in half the time, so its speed is double at 0.2 tasks per second. Now we take the difference to find the extra speed and divide that extra speed by our original speed from the slower task and multiply that by 100 to get our final answer of 100% faster. So I believe this is the actual way to calculate how much quote-unquote faster an algorithm is over another, and this is the method that I used in order to get the numbers that you saw in the thumbnail of the video. Okay, back to the show. If A star takes longer than the pressure pathfinder, we'll get a positive percent, meaning that we saved time. But if A star takes less time than the pressure pathfinder, then this whole number is going to be negative. Then that means it's actually slower than A star. Let's try our maze again, and boom. Oh, that looks sick. Let's try with a few more kind of random patterns. And of course, you know, we could be testing this more rigorously, but honestly, I don't really care to right now. I feel like this is a okay enough shooting from the hip test, you know, if you get what I'm saying. If it's really not that neck and neck, I feel like it's kind of conclusive anyways. I think that's good. Let's test it again. Uh-oh, did we break it? Aw, man, I think we broke it. Oh, well, let's try again. Oh my gosh, I just figured it out. This is the trickiest bug ever. I really got caught with my hand in my pants with this one. Yeah, I tried to do some fancy stuff with this and that, but that's a fun part about programming. Making arbitrary problems for you to spend your time solving. Yep, anyways, let's get back to our highly scientific and rigorous test as usual. Ah, dang it, I think we messed it up again. Cut! Take 15. Let's do this one more time. And I thought for the last few tests, we just do some pretty symmetric shapes. There we go. Wait a minute, am I calculating this all wrong? Oh, hang on. I think I got my math wrong again. I'll be back. Okay, yeah, I did my math all wrong. I just calculated the average in a really weird way that led to probably complete total nonsense for the past hour that I've been tinkering around with this, but that's how it is sometimes. Well, that'll change the way I edit this video in the future. I wonder if we cast this to a float? Nope, I don't think that's the problem. Oh my gosh, total rookie mistake. This is the same as this. I feel so stupid, but I'm also so tired. My brain is so tired. Check this out. I even gave those lines to ChatGPT, and it didn't even realize that I was assigning the exact same thing to both of them. I'm like, what is going on here? Why am I getting 0? And it just gave me the spiel. Oh man, maybe its artificial brain is tired too, and it needs to go to bed. All right, let's do this one last time. This is actually kind of crazy. It's still 82% faster than A star when it's only calculating one path? What? That's actually insane. I'm actually really curious now to see how will they do in comparison when we make A star calculate all the paths again. Anybody remember the Spooder Man? I'm not the programmer this world wants. I'm not the programmer this world needs. But I am the programmer this world gets. Okay, I really gotta fix this error. It keeps messing up my tests. I use that null coalescing operator again. Elegant and simple. I don't speak French. Okay, let's give this a proper final test. So it looks like overall the tests there, it seems to average out pretty consistently around 96%. So this is the actual number that I will use for the thumbnail. 96.48193% faster than A star. I finally beat my coding nemesis. And of course, if you don't think my testing methods were good or my comparisons were unfair in any way, by all means, make your case in a comment and correct my math. I'll also be posting this project and my previous nuclear physics simulator project on GitHub as per popular request from the last video. So feel free to do any testing you want to on your own and report back results. The last thing I wanted to do to round out this project is to figure out the big O complexity of my algorithm versus the A star algorithm. So I did a little bit of math and digging through the interwebs behind the scenes, and I've basically come up with this. For anybody that doesn't know what big O notation is, it's a way to conceptualize how much time an algorithm takes as the number of parameters scales up. Let's consider a pressure pathfinding algorithm first. I'm estimating how much time it will take by keeping track of how many times we're using a single tile in our computations, which might not be perfect, but it'll give us a rough idea. With respect to the width of this empty grid, it has roughly a complexity of n squared. On the other hand, if we're considering A star, and this is our simplified version of A star, the function I found for calculating this is f of n equals 2n cubed minus n squared, which gives us a complexity of roughly O of n cubed. You could also do this with just the regular A star pathfinding algorithm. The calculations for the function get a little more complex, and I couldn't really find a function that fit this on my own, so I actually gave it to O1 Preview, and it actually did find one that works. It's this 4-term polynomial 3n to the 4th plus 13n cubed minus 27n squared plus 17n all over 6, which gives us an even bigger time complexity of n to the 4th. With that in mind, I pulled up Desmos online and had those functions graphed. This green line is our pressure pathfinder performance, red line is the simplified A star performance, and the orange line is the regular A star performance with no simplification. This gap represents how much more performant the pressure pathfinder is over the A star pathfinder. So in Unity, we were mostly experimenting with a grid size of 10, and if we see where 10 is on this graph, it's right at 100 because 10 squared is 100. The point where A star hits 10 puts it right up there at 1900. And if we go to the calculator and do our efficiency math from before, 94.7%. And that's roughly on par with the numbers we were getting before of about 96%, but with an empty grid size of 10, we get almost 95% more efficient, just from a mathematical point of view. So I think that's super interesting and exciting to see, but there's just one point that confuses me so much. You see, I'm used to having a brilliant idea and then realizing that someone has already capitalized on it before I have. Like that time that I thought of paddleboard stabilizers on the side so that you could take a nap without worrying about tipping over, or that other time when I thought I should invent an attachment for laptops that adds extra screens to it. Yeah, different people did those things and are already making bank off of them. What just confuses me, if this is so much faster than A star, especially for video games, why aren't more video games using this? Or something like it. It was so simple to implement. So of course, that's why I can't help but wonder if somebody has already done this and I just don't know about it. Somebody tell me if I'm being delusional and somebody else has already done this before I have. Somebody tell me. What am I missing? Digging on Wikipedia, taking a look at all the videos on this topic, they just all seem to be about A star. So many different variations on A star as well. There might be some that are similar to what I'm doing here, but I mean, I just don't have the time to digest all of this information. This random guy's blog, this is just another way to use A star, where instead of using the entire, oh wow, I can actually draw on that. That tripped me up. This one simplifies it by using waypoints. This is actually pretty fun. So again, if I am missing something very obvious here, please tell me. But if not, hey, go ahead and use it for your game, man, and see what you find out. I don't want to go around touting that I've discovered something that I haven't, but at the same time, I'm completely baffled that games aren't using something like what I made today. Well, I guess if nobody's using it in their games, I might as well put it in mine. So, is it bad to use AI in your coding projects? Well, it really depends on your goals. If you want to code for the sake of coding itself, then of course, don't let AI take that from you. If your goal is simply to turn your idea into reality as fast as possible, then I see no problem with it. My goal is to inspire you to learn something new and build something awesome, and whatever accomplishes that better is what I'll aim for. So go to the pinned comment under this video or the poll I posted on my channel, letting me know what kind of workflow you prefer to watch. この作品が気に入ったら、僕の原子力物理学シミュレーターのビデオもぜひ見てください。それではまた。走れかけろ